So it's remove or short circuit?
Short circuit.
Short circuit. What do you mean by remove? We just take it off. Just remove it. Okay. So if that's what you mean by remove, that means basically we have opened that capacitor. Because you just take it off, right? So you just open that part of your circuit. But basically, if we are talking about high frequency, if you can remember, when we talk about AC analysis, high frequency basically is AC, right? Signal must be AC. So we can talk about frequency, right? So high frequency basically is we are talking about AC signal. So if you can remember, for AC, if we are talking about AC signal, all the capacitors in your circuit is treated as a short circuit, right? All capacitors are short for AC. So for high frequency capacitor is equivalent to a short circuit. A low frequency?
Open circuit.
Okay, so low frequency basically capacitor is like an open circuit. So how to remember this one? Here basically is a revision for your previous part. Okay, for high frequency capacitor is like a short circuit. Low frequency capacitor is like an open circuit. Basically, just look at the capacitor symbol. This is your cap, right? You can see this part and this part basically they are separated because in between there is nothing. Okay, so if you still remember, when we do DC analysis, if we got transistor circuit, and if we want to do DC analysis, we just treat the circuit like this, right? We never change the transistor into other circuit, right? So basically, what you draw here, the symbol is what you DC see. Okay, so if your capacitor look like this, I mean the capacitor symbol is like this, that means your DC see this capacitor this way. So for your DC cannot pass, right? There is nothing in between, they are not connected. So your DC cannot pass. So for your DC, or you can say it's a low frequency signal, because the DC, the frequency is very low, right? It's almost zero. Okay, so for your DC, the capacitor is like an open circuit. So AC is the opposite way. So that's the previous part. That's just a revision. So but the question now is, for previous part, we only talk about for high frequency, your capacitor is like a short. For low frequency, your capacitor is like an open. So what's next? What will happen after I really short this capacitor, or what will happen after I really open this capacitor? We never talk about this, right? So this part is to tell you what will happen after you short the capacitor or you open the capacitor. Because what we did before is we just assume all the capacitor can be short in high frequency. Okay, all capacitor can be open in low frequency. So we want to know what exactly will happen after you short it and open it. The actual effect. Okay, so this leads to the key idea of these two methods, your SCTC and OCTC. So the key idea of these two are actually to see what?
To see which capacitors reduce the gain.
Again?
See which capacitors reduce the
Yes.
gain of the.
The key idea for these two methods is actually to see which capacitor
Reduces the gain of the transistor.
reduces the gain of
The circuit.
the circuit, right? Or you can say of the system, or you can say the circuit. Blah, blah, blah. Because once you are given a circuit, or once you are given a system, there will definitely be there will definitely be the output and the input, right? So if you take the output over the input, no matter what how the system look like, you will get your transfer function. And the transfer function is basically the game. It's the same as the idea is the same as the game. Okay, so the key idea of these two parts is actually to see which capacitor will contribute to the reduce of the gain of this whole system. Because previously we only treat capacitor as short for high frequency and capacitor as open in low frequency, but we never talk about what will happen after I treat them as open or short to the gain. We never talk about what will happen to the gain, right? So this part is to see what will happen to the gain and which capacitor will reduces the gain of your system. Why we need to care about this capacitor? Why we need to care about capacitors which reduces the gain of the system?
And we can remove it.
No, we can never remove it. It's given, it's a circuit given to you. You need to analyze. But why we care about capacitors which reduce the gain of the system? Why we never care about the capacitors which increase the gain of my system?
Because we're supposed to amplify the gain.
No. Why we only care about all these capacitors which reduce my gain?
More gain is better.
More gain is better. No. What's the purpose of these two methods? These two methods is to help us to find what?
Troublemakers.
These two methods is actually to help us to find what? What's the final result for this? What's the final target for this? By using these two methods. Why we use these two methods? I mentioned
Frequency
before, right?
response.
Find the
Find the omega.
trouble capacitor.
no. Why we need these two methods? We need these two methods to help us to find the 3 dB cutoff, right? We need to find a higher cutoff and lower cutoff. That's our final goal, right? So basically these two methods, no matter how complicated it is, the final goal for this method is to help us to find a 3 dB cutoff. So what is so special about this 3 dB cutoff? This 3 dB cutoff is once my gain, the plot, hit the 3 dB cutoff, it will start to drop, right? Okay? That's why I want to find a capacitor which causes the drop of my gain. Because that capacitor is responsible to the drop of my gain. If that capacitor is responsible to the drop of my gain, that means that capacitor contributes to my 3 dB cutoff frequency. Right? That's why we need to find this troublemaker capacitor. Because all these capacitors will cause a drop of my gain. So they are contributing to the 3 dB cutoff. And my final goal is to find the 3 dB cutoff. So I need to find this capacitor first. Okay? So here another recap. For this part, we not only need to take care of all the capacitors given to you, I mean all those external capacitors drawn in the circuit. We also need to take care of all the parasitic capacitors. Because your transistor, due to its physical structure, there will be some parasitic capacitors inside your transistor. No matter how you try to reduce it, you cannot reduce it, it will be there. Once it is manufactured, there will be parasitic capacitor. Okay, so here is another recap. Where are all those parasitic capacitors for your transistor? For MOSFET and BJT? Usually when we draw the transistor, we just draw them this way, right? But it should know where are all those parasitic capacitors. Where are your MOSFET parasitic capacitors?
Between the source and the gate.
So it is called what? What's the name? What's the name for this capacitor?
CGS.
Okay, so basically it's CGS because it's between the source and gate. So it's CGS. Another one?
Drain and gate.
Drain and gate. So it is called
CGD.
CGD. I got one more. One more.
CDB,
CDB. So it will be between where?
drain and between the
Between the drain. D is drain. Where is B?
base.
Where is B? Base.
A. No base.
Ground.
Ground.
Where is this base? Is it always a ground? I know when you draw a transistor, because we only draw the symbol, so inside the symbol there are only 3 terminals. But if you draw the full symbol, I mean there is another full version for this transistor symbol, it is actually 4 terminal. Here is the base. Terminal. It is a 4 terminal device. But for simplicity, usually we just ignore this base because for all the NMOS, this base is always connected to the ground. And for PMOS, this base is always tied to the VDD. So we usually ignore this one, but you should know there is a base. Okay? So because this one is NMOS, so your base is tied to the ground. So here is a ground. But if this one is a PMOS, this base is tied to VDD. Okay, but this VDD is what? This VDD is a DC, right? When we talk about power supply, VDD is a DC. But when we talk about capacitor, when we want to talk about capacitor, usually we are talking about
AC.
AC, right? So no matter what VDD or ground you are tying your base to, this terminal is always a ground, AC ground. So these are the 3 parasitic capacitors for your MOSFET. BJT, parasitic.
Base and collector. Between base and collector.
Between base and collector. So this one is what's the name?
C mu.
C?
Mu.
C mu. But one more.
And between base and emitter,
Base and emitter.
C pi.
C pi. So for your BJT, because the physical structure is different from MOSFET, so it only has 2 parasitic capacitor. One is C pi, one is C mu. How do you remember this one? This one is easy. C pi, because it's between base and emitter. If you still remember the AC small signal equivalent for this BJT, between B and E there is a
R pi.
R pi. So correspondingly, this transistor, this capacitor is called C pi. So that's the revision. So for this part, you need to consider all these parasitics basically, because they are capacitor, so they will contribute to your frequency response. So basically, these are the basic knowledge, basic idea of these 2 methods. So how to use these 2 methods? You not give one example, like what I draw there. So how to use these 2 methods? To find my 2 cutoff frequencies. Let's say I want to find the high frequency cutoff, so I need to use SCTC, right, for high frequency cutoff. So how to use this method? How to use your SCTC?
Short for the capacitor on. short the capacitor here, then
Wait a minute. What's the first step? If you are given a circuit, then they ask you to find the two cutoff frequencies. What's the first step?
draw the small circuit and then see some.
No. They only want you to find the two cutoff frequency. No,
AC.
AC.
no. What's the first step? No. The first step is to add in your parasitics. Because all the parasitics will not be drawn for you. You need to draw by yourself. Okay? So the first step is to add in all your parasitics. So basically here is your CGS, here is your CGD, here is your CDB. So first step, if the question is only asking you to find the higher and lower cutoff frequency, the first step is to add in your parasitics. Okay, what's the second step? Is to use the method, right? So how to use the method?
Analyzing AC first, so must change the one to AC.
No. Always remember, this method is a shortcut. Shortcut means what? It provides simplicity to your analysis, right? So if you need to draw, you need to replace your transistor by its AC equivalent. It is a full circuit analysis. It is not a shortcut. So how to use these two shortcuts?
Short circuit.
Short circuit, which one? Let's say first we want to find a high frequency cutoff pole. So high frequency is to use your SCTC. Then SCTC. Then what's next? What's next? How to use your SCTC?
You just keep the capacitor.
Sure, which one?
The one on the right side first.
Can you summarize the whole idea?
If you short one, then the rest you have to open.
I short one, then the rest are open. Then
Then you analyze.
I analyze what?
Analyze whether the
Find the R in.
No.
analyze whether it will lower the.
Yes. The key idea is to see, you need to see capacitor by capacitor. Okay, so maybe we start from this CC. So we only want to care about this CC, right? We want to see its effect. Okay, so we only keep this one. Then we remove all the other capacitor. So how to remove? Is we just take them out. We just take them out. We assume they are not there because we only want to see the effect of your CC. So I assume all the other capacitors are not there. I just leave my CC there and see what's its effect. Okay, and because now we are talking about what? High frequency. So in high frequency, a capacitor is like a short circuit, right? So after I take out all the other capacitor, I only have my CC. And because it's a high frequency, we are talking about high frequency cutoff, so I short my CC. Okay? After I short my CC, then what's next? The next is to see what's the effect of shorting this CC. What's the effect of shorting this CC to my circuit? How my circuit gain will change? How my circuit gain will change? Because we care about the gain, right? If the gain starts to drop after I short my CC, that means my CC is a troublemaker. Okay? So how to see? Now I short my CC already. How to see whether my gain change? Whether my gain reduce?
Replace with a test voltage.
No. How to see its effect on my gain?
Must find the R in.
No. How to see its effect on my gain? What's the gain equation? What's the gain? What's the gain equation?
V out over V in.
Okay, gain equals to V out over V in. So where's my V out? V out is here. V is here. What will happen after I short my CC? How will my V out over V in change? Originally I got capacitor there. And now I'm shorting it. So how will my V out over V in change?
It won't change.
It won't change. Is that true? How will my V out over V in change? Use the intuition. Because this method is a shortcut. So it got nothing to do with circuit analysis. It's all about common sense and intuition. You just look at the circuit and see what will happen to this V out and V in. What's the difference? Originally I got a capacitor here. And my V out is there, V in is here, I got my V out over V in. But now I'm shorting this capacitor, that means now there is no component in between these 2 points. There is only one line.
Nothing
And
else.
here is my V in, there is my V out.
Nothing happened.
Huh?
Nothing happened.
Nothing happened.
Yeah.
Is that true?
Yeah.
So I think less impedance.
That's impedance. So
So
we are talking about high frequency, right? So originally here got a capacitor. Capacitor is in high frequency region, it is like a impedance, right? It got its own impedance. Okay? So originally, which means that originally here got impedance, or you can say you have a resistance here. But now I'm shorting it. That means now there is no resistance here. So what will happen to my V in?
Oh,
Will increase, right? Why?
Lower impedance, then the voltage will allow more control.
Less voltage drop from V signal.
Strictly speaking, it is a higher portion of your V signal will be
Transfer.
transferred to V in. Why? Because originally you got components here, right? You got a resistor here, so you will take certain voltage. So your V signal start from here, then go across this R signal, it will drop. Then go across this CC, it will drop again. Then it comes to your V in. But now I only got one R signal. So your V signal will only drop once, then to your V in. So that means now your V in will increase. Your V in will have a higher share of this V signal. So if a V in is having a higher share of your V signal, what will happen to this V out over V in?
decrease. Small.
Is that
Gain
true?
will decrease.
but then your VR also will increase
Yeah, must see my
simultaneously.
But we're not ignoring that side, right? Or we're not?
We are not.
Oh, I thought we were going to.
No. We were only ignoring all the other capacitors.
Oh, okay.
So now I know after I short this CC, my V in will increase. So what will happen after my V in increase? The rest of my circuit is still the same as before, right? So that means my V in will still be amplified by certain amount, then give my V out. So that means my V out over V in is actually my V out over V in is actually
Increase.
increase. Are you sure?
Increasing.
It is actually about the same, right? It's like your originally you got amplifier which can amplify your signal by 5 times. Now I input a signal which is 1 volt. The output is 5 volt. Now I increase my input signal to 10 volt. What's the output? It's 15 volt, right? But the ratio is still 5. Because my amplifier, the amplifying ratio, the gain is still 5. My amplifier itself is not changed. Okay. But sometimes, of course, the gain of the system will be affected by the impedance on the input side. But relatively, the output of the input is about the same. So that means what? That means after I short my CC, my gain is actually not reduced, right? I mean, The only thing I can confirm is the gain will not reduce. Whether it will be the same as before or it will be higher than before, I don't know. I'm not very sure because I'm using the shortcut. I don't want to do all those complicated analysis. The only thing I can be very, very sure is the gain will not reduce. Okay, so if the gain is not it's not going to be reduced, that means my CC is not a troublemaker. If the CC is not a troublemaker, that means it will not contribute to my holes. It will not contribute to my cutoff. Okay, so that means what? That means we can
Ignore.
just leave it.
Ignore.
Oh, yeah, we can just leave it.
It doesn't affect.
You can just take out cause no
You
need
just
to
take out.
like no need analyze this capacitor.
Okay, we just put it back, but you need to remember because we are still going to analyze other capacitors, right? So we want to draw our original circuit first, lah. I mean, resume to our original circuit first. So we put back this CC, but you need to remember this CC is not a troublemaker. That's all. We put it back because we need to analyze other capacitor. So we want to resume to the original circuit. Okay?
So we redraw the circuit, then we can just take out that one. Like we redraw
No, you never take out components.
like the capacitor like or like
We don't need to take out component. For this part, it's just help you to find the cutoff. We are not doing the full circuit analysis. We only want to find which capacitor is the troublemaker. So we are not taking it off, we are not putting them in. We only want to see which one is the troublemaker. Okay? So we put all the capacitor back. Your CGS, your CGD, and your CGD. You put all the capacitor back. So we use the same method. Okay, because we finished CC already, we know it's not a troublemaker. So maybe I need to pull that. So it is not a troublemaker. So we go to next capacitor. Let's say for example your CGS. Okay, if I want to see the effect of CGS, how should I do? We do the same thing, right?
Short circuit.
What's the first step?
Short circuit.
Short circuit where?
CGS.
Okay, so if I want to see the effect of my CGS, I short it. Then,
Again we redraw.
how about the other capacitor?
Repeat.
How about other capacitor? Open, right? Just take them off. Remove. So now I got this circuit. So what will happen to my gain?
Equals 0.
Why?
Because you just grounded.
Why? Can you all see that? Okay? Because your VIN is now shorted to ground by this CGS. So that means there is no VIN. There is no gain already. Okay, we are not getting any gain. Because your basically these two terminals are short together. You are not having a you are not having a transistor even. You are just having a diode here. Okay, so now you don't have any gain. That means the CGS is troublemaker, right? Then you need to remember CGS is a troublemaker. Then you put everything back again. Okay, you put everything back. Then next, maybe you want to analyze CGD. So
the rest open.
So I open the rest, remove. CGD? How about CGD? Short. Okay, so I short my CGD. So what happened to my gain?
Connected to your VDD.
What happened to my gain? Oh, by the way, one thing forget to mention. Before you do all this, you need to remove all your DC sources. Because we are doing AC analysis, we are doing high frequency. So you need to remove all your DC sources, which means that VDD is a ground, and ground is a ground. Okay, so here is a ground.
So
So B is also 0.
So after I short my CGD, what will happen?
K equals 0.
Gain is not equals to 0.
There will be no V.
No V,
No. What's the gain now? The gain now is 1. Why?
V in directly connected to V out.
Because the V in is connected to V out directly. V in is short to V out, right? So V in equals to V out. So the gain for this system is 1. So that means originally I have some gain, but now after I short my CGD, the gain dropped to 1. That means my CGD is
Troublemaker.
a troublemaker. Okay? So you remember CGD is a troublemaker, then you put it back. Then you do all the same analysis again. You put back, okay? So maybe now you want to do the CDD. Then you open the rest. Okay, open the rest. And CDB you just shut it. Here, you just shut it. So what happened to the game?
Gain not a factor. The gain is not a factor.
The game is not a factor, are you sure? What happened to my V over V in now?
Oh, V out.
What happened to my V over V in?
V out will increase.
Hmm?
V out will increase.
No. Can we see directly from the schematic? What happened to my VR
V
over
out
V?
will go the shorter.
My VR is connected to the ground now. Can you see that? VR is here. VR is connected to the ground. So VR is short to the ground. So no matter what input, what bit in it is, my VR will always be 0. That means the gain is always 0. That means my gain is actually dropping. Okay? So CDB is another troublemaker. Then you need to remember, then you do the same thing to your CL. The CL is here. As you can see, your CDB and CL are actually in parallel, right?
So they are
So
CL is
they're
also
actually having the same effect. Okay, so if you short your CL, your VR will be connected to the ground. So the gain is actually dropping. So the CL is actually another troublemaker. So now we put all the capacitor back. After you get all the troublemakers, you need to remember